Hello, everybody. This is Professor Ma, and this is the sections of the converging and divergence of series. Remember, series are adding infinitely many numbers, and we want to decide that their sum is finite or infinite. Okay, and one is called convergence, and the other one is called divergence. And in the problems that we are going to do actually involves proofs. So which is a mathematical, which is a tradition in mathematics. In fact, if you go in mathematics, more and more stuff are involved proof. That is airtight justifications. Okay. And what we are going to do is we are going to be presented with series, with the problem of deciding which series converge, which series diverge. And we are not going to calculate what the actual sum is going to be. Those problems are, for most of the problems that we have, it will be impossible to find a nice quote formula, closed form for the answers. So let's first talk about what the protocols are for dealing with this problem. The protocol basically we have to declare the sum, the series we have in hand is either convergence or divergence, and then the second things we're going to do is we're going to prove our declarations. Okay, and both of these steps basically is kind of a chicken and egg questions. I mean, in order for you to declare it's converging or diverging, you kind of have to know the series, how it works. Okay, and both of these basically to recognize the series, which one converges, which one diverges, are based on the following things. First is based on a list of series that we know the behavior. The ones that we already know the divergent, convergent, certain type. Okay, and then from there we have a bunch of strategies which we will verify our declarations. Okay, and so in particular, we're going to talk about series of positive numbers. All the entries are positive. And if we have that totally clarified, then the different type, another type of series where the signs are plus, minus. And then, but the discussion of the convergence or divergence of those types will be very easy to sort out. Okay, once we know what's happening in the positive ones. Okay, so these are the basic facts we are going to assume going in. So we already talked about these. In the case of geometric series, we can actually find out what a sum is if we're going to just use R less than 1. So remember, we assume R positive. If you like, we can put an absolute value around it. Okay, but again, we're assuming positive. But eventually, we will have absolute value. Okay. We know when these converge, geometric series converge diverge. And the second type is a P series. When the P equal to 2, then it will be 2 square, 2 square, and this 3 square, 4 square, 5 squares, everything square in the denominator. And then P is bigger than 1, then converges. But P is less than or equal to 1, then diverges. And in particular, at P equal to 1, it diverges, the sum is infinity. Okay. And so presented with a series, then here's the first step you do. You make sure the term goes to 0. If the term doesn't go to 0, there's no point. Like for instance, 1 plus 1 plus 1, if each term becomes doesn't go to 0, then they're going to add up to infinity. Okay, so that's a priori, for the condition in order for to possibly converge, you must have these terms all go to 0. Okay, and then the second thing you're going to do is you're going to look at the formula. You're going to trim it down. Okay, And you say, what do you mean by treatment? You will see, because we are going to have a theorem actually in this discussion, say, how do we treatment? Basically all the non-essential term, we're going to throw it away. So we have a cleaner, the core of the formula, and we use that as a comparable copy. Okay. Of course, this is where the work is. We have to justify that the things we created is comparable. And then we take the comparable copy, which is supposed to be now simple, with all the things is trimmed, and clean. Okay, and then we're going to apply all kind of tests and or invoke the list of series that we know the behavior, geometric and the P series, and to use that to infer what happened to our trim versions, what is converge or diverge. Okay, but this step, when we justify it's comparable, meaning that these AN behave exactly the same as BN, therefore the conclusion to BN I can use it to conclude AN. Okay. And in this process, I want to remind you that we have this for n for n integers. Okay, n become large, then the factorial is bigger than power. Okay, bigger than exponential, bigger than the power, bigger than log. That's the meaning that if I divide them, they go to zero, they go to infinity. But if I form fractions of them. And secondly, and the bulk of the works for the homework on the test is justifying limits, calculating limits, because a lot of these tests that we're going to encounter involves taking limits. Okay, so here we go. The root and the ratio test. Okay, so again, remind you of the positive series. And the one thing about geometric series is that the ratio between two terms are fixed. So I have Rn, and then to get next one, I get times R, Rn plus 1 times R times R. Okay, to get Rn plus 2. So that means if I have a series of with terms sum of An, with term, if I take the ratio of the two terms, An plus 1 divided by An, and is R in the case of geometric series. But I don't really need that to be exactly R equal to R. I can have the limits. Okay, so if the terms ratio test says if you take the ratio of terms one after another, if the ratio becomes more or less stable, equal to some R, then this particular series is almost geometric. Okay, you might have some components that in there that's you don't doesn't quite fit. Has little bits in there. For instance, this one. In comparisons, n cubed to 2 to the n power, 2 to the n power is a exponential. N cubed is a power function. So 2 to the n and divided, so it goes to infinity a lot faster than n cubed. Okay. So here. So we divide everything. Okay. So first, so we can do the ratio test in this case. Okay. So the algebra, usually what you can do is we write down what the An plus 1 term is. It's right here. And then instead of writing it divided by An, and we just flip An over. So actually reciprocate these, flip and multiply. Okay, do the algebra. Okay. And then here is the limit problem, which I'm saying, then we take the limit of these as and leave this part up to you. And this actually is what you need to do on homework, on the test, to justify these limits equal to something. In this case, the limit is equal to 2/3. Okay. So in other words, that basically this series is almost, you can disregard the n cube portions. Basically, it's like 2 to the n divided by 3 to the n. In order to get next one, you multiply by 2/3. You see, and n cube is insignificant as n become bigger and bigger and bigger. Okay, because the exponential function is a lot bigger than power function. Okay, okay. Hence, this is almost geometric with r equal to 2/3. Hence, it converges. Hence, the original converges. So, I mean, yeah, hence the series converges. Okay. And the other characteristic of the, a word about what happened when you use the ratio test and you wind up with the ratio equal to 1. Then the answer is when the ratio is 1, we couldn't identify. The test itself failed. For example, harmonic series, the ratio is 1. Okay. The p series for n squared in the denominator, the ratio is also 1. But we know by our knowledge, this one, harmonic series, sum of 1 over n, this is infinity. On the other hand, sum of 1 over square is finite. But in other words, by having the limit equal to 1, I don't know which way it is, whether it's infinite or finite. So the test failed. Another characteristic of the geometric series is if I take the nth root of geometric series, and geometric series of terms r to the n, so nth root is equal to r. I get the ratio r again this way. So I can, gives us the root test, basically very similar to the ratio test, except this is, you can take in this one, you take roots of the terms. Oh, notice there's no ratio of 2 terms. You just take the roots of the nth terms, 1 over nth root, or n to the 1 over nth root, whichever way you want to write it. And when do we use these? Well, we use these when the formula after nth root, it can be somehow the main part of the formula, it can be extracted nicely with nth root. Okay, the algebra comes out nicely if I do nth root. Okay. And so since this involve nth root, so this we're going to assume. Okay, and so in fact, yeah, I put this one on the test, okay, to ask you to verify this. So we are going to assume that this is, since nth root of n to the kth power, like any polynomial n squared, n cubed, you take the nth root, the limit is going to be 1. Okay, so we're going to invoke that somewhere along the way. So here, there's a problem. Does this one converges? Well, notice 3 to the n, it's, if I replace this by the nth root, then it's 3 comes out. Then the question is, of course, what's the limit of the top goes, of n to the 3 to the n, 3 over n, and that's what we invoke. This says, oh, the limit of that is 1. So therefore, the nth root is 1/3. Okay. In other words, this series is really, it's really, the top n cube is so insignificant, in other words, in some sense, there's really no differences from summing 1 over 3 to the n. Okay. in this sense, it's related. Okay, it's almost geometric, if you like, because the top part is really insignificant compared to the bottom part. And this converges, okay, because this is the roots is less than 1. Okay. Now, then finally, this is actually the part that we are going to, the theorems we are going to use to, when I see a problem, this actually is the first things we will, you should do, okay? What? Well, that is, given the problems, you want to throw away the parts that's not important. What are the important parts? The important parts are the dominant terms. Usually these formulas are in fractions, so you want to find the part that's the biggest on top and the biggest on the bottom. Okay, and you want to throw away the other parts that's not important. But how do we justify these? We justify these using this ratio comparison test. Okay, so we say two sequences are almost multiple of each other. So if the limits of term by term ratio becomes constants, then y is almost c, in this case, bn is almost c times an. If I multiply an cross side, go to the other side. So therefore, these two sequences are almost multiple. Okay. And the two series are almost multiple if the sequence themselves are multiple. Two sequences are almost multiple. And the limits or ratio comparison test says, oh, if two series are almost multiple of each other, then they behave exactly the same. If one converges, the other one converges. If one diverges, the other one diverges. Okay. What is this good for? What is good for throwing away the parts we don't want? Like for instance, if I look at this in a problem and say, oh, does this sum converges or diverges? Okay, and the part that's not important as n goes to infinity for the top, the 2 is not important. So therefore, I say, oh, I really don't want this 2. I mean, I really don't need to consider this 2. And in similar manners, well, this n minus 1, it's really becomes insignificant compared to n squared. So I want to throw away that part. But the ratio comparison test says you have to justify these. And this is the bulk of the work, to justify what's left is comparable to the original. So I'm going to let this to be called an. And I'm going to throw away all the other parts. Okay, that is all the parts that are important, even the 4. I'm going to let that bn just to be n to the first power n squared. Those are the dominant, these are the two dominant terms. And I'm going to take the limit of the ratios. Okay. So again, dividing by an, just flip an over. So the algebra, just flip this one over and reciprocate it and calculate the limit. The limit is 1/4. Okay. On test, you need to justify these. Okay. Give me a reason for doing this. L'Hopital's rule or cancellations. Okay, so on the other hand, Bn, this simplified version is actually harmonic series, so it diverges. So therefore, go back to original, it diverges also. Okay. And similarly, in this problem, we can throw away the parts that's not important, which is this and that. And so we can pull out, we can compare this basically to 3 to the n squared on top and bottoms n to the 7/2. Okay, so first things is I do this simplification. I justify saying, oh, I can simplify this formula down to this formula. And okay, so we're going to set Bn to be just those terms. Now I'm going to take limit of Bn over An. And in this case, again, you have to show these limits. And I believe this for you in the homework on the test. Okay. Okay, so the limit is a positive number. So therefore, one is the multiple of the other. In other words, Bn basically is 1/3 of 8 times An in a long run. Okay. And so A and Bn, the series converge, behave the same, but it's a lot easier to sum Bm. That's the P series, okay? The P series with P equal to 3/2 and P bigger than 1, it converges, right? In the denominator. So therefore, the original series converges. Okay. So these are the basic strategies, okay? And of course, you also have other strategy, which is you can find an easier formula X as a ceiling for trying to demonstrate things converge. Ceiling, make a ceiling to show convergence, or if you want to show divergence, come up with a bottom, a floor that pushes yours to divergence also. Okay, so those are the other tricks. And okay, that's basically it. Okay, basic structures of verifications by series convergence divergences. Okay, bye-bye.